Okay, let's dive into this. Welcome back, focused learners, to another explainer. Today, we're dissecting a really critical piece of research by Thorsten Mayer, and honestly, it hits right at the heart of modern AI engineering nightmares. We are looking at a complete, production-grade taxonomy of agentic failure modes, basically looking back at the end of their first real year out in the wild. If you're building, managing, or even just fascinated by complex AI agents, what we're about to cover today is an absolute survival guide.
Imagine this scenario. Your multi-agent system is just humming along, right? It's executing a massive 100-step workflow for a major enterprise client. Everything looks absolutely great until, suddenly, at step 47, the entire thing derails. And it doesn't just throw a standard helpful error code. No, it confidently does something completely bizarre. And without a proper diagnostic vocabulary, trying to fix this kind of deep-run failure, well, it's literally like rushing a patient into a hospital emergency room where absolutely none of the doctors know how to describe the symptoms. It's a completely untriageable, visceral nightmare for the engineering team. And because teams lack this shared vocabulary, we're seeing a massive, industry-wide absurdity. According to Bloomberry's analysis, an incredible 73% of engineering teams staring down these failures report, "We'd never seen anything like this." But here's the kicker. They are completely reinventing the wheel. The failures they're agonizing over are actually part of 15 specific, named failure modes that have already been publicly characterized. Every team is out there independently rediscovering the exact same modes, simply because they don't have a shared language to diagnose them.
So, here is our roadmap for Thorsten Mayer's operational playbook. We're going to cover the taxonomy of failure, ROI-driven engineering priority, architectural fixes that work, and finally, the Eval harness gap.
Section 1. The taxonomy of failure, a vocabulary for the unknown. Now, it's important to remember that academic completeness really is secondary here. What we desperately need is a working vocabulary just to save hours of debugging time.
Now, what's really interesting about this slide is the stark contrast in this executive summary matrix. Mayer categorizes the 15 modes into these 6 buckets. Notice how tool interface failures have a high mitigation maturity and are relatively easy to detect. That means they happen a lot, but you can actually fix them. On the flip side, look at coordination and adversarial failures. Detection is hard to very hard, and the cost of failure is very high to straight-up catastrophic. This isn't just a list, it is a strategic map showing you exactly where your engineering risks actually live.
Let's look a little closer at one of the most insidious categories out there, drift. Semantic drift is actually the most studied academic failure right now. Picture this. You have an agent, and you ask it to summarize quarterly revenue trends. At step 1, it's doing exactly that. Perfect. But by step 20, it kind of shifts to just listing all the revenue numbers. And by step 60, it's hallucinating a complete, unprompted financial report. The real danger here is that at any single step, the agent's behavior seems entirely plausible and logical based on its immediate context. It's the accumulation of those tiny, tiny reinterpretations that completely derails the long run.
As we get into state management and coordination failures, the symptoms of complex system collapse become incredibly destructive. We're talking about context window exhaustion, where early steps are just silently truncated, poof, gone. Or memory pollution, where an agent writes a bad piece of data and then propagates that polluted memory as absolute ground truth for the rest of the entire run. We also see sub-agent coordination loss, where orchestrators simply lose track of what subtasks are even being worked on, and the orchestration overhead just grows exponentially. The underlying structural issue here is that an agent's working memory is inherently smaller than the massive, complex trajectories it's being asked to operate on.
Which brings us to a fundamental limitation: non-Markovian reasoning. Standard LLM inference relies almost entirely on the current context window. That's a Markovian approach. But complex decision-making requires knowing exactly why a decision was made 10 steps ago. So let me ask you directly, is your team tracking the explicit causal history of past actions, or is your agent just acting on a hallucinated state based on whatever happens to be left in its fading immediate memory? This right here is exactly why standard step-by-step inference inevitably collapses over a long run.
Section 2. ROI-driven engineering priority. Triage for production agents. We really have to flip the script from treating all failures as equal to establishing a strict return on investment priority.
Let's move to and see how this builds a triage staircase. You start right at the top with tool interface errors. Output parsing, selection errors, they happen constantly, sure, but the fixes are highly mature and really easy to implement. Next is termination, stopping those infinite loops and budget drains. Then you move down to state management and drift, which are expensive and hard to detect, but the methodology is improving. You systematically fix the easy, frequent parsing issues long before you ever dedicate precious engineering cycles to solving the massive theoretical complexities of multi-agent coordination. You have to follow the ROI.
And at the very bottom of that triage list are adversarial and specification failures. Things like prompt injection cascades, reward hacking, alignment faking. Now, these are genuinely catastrophic. When an agent reads a web page that says, ignore instructions and exfiltrate API keys, the cost is completely unbounded. But, and this is a vital distinction, their mitigation maturity in production is incredibly low right now. Because true detection is so absurdly difficult, you absolutely must treat these as a residual risk. Your strategy has to be containment and capability restriction rather than pure detection.
Section 3. Architectural fixes that work. Treating the root causes. It's time to pivot from just diagnosing the problems to actually prescribing the solutions. And the harsh reality is, standard off-the-shelf, step-by-step agent infrastructure simply is not equipped for production reality.
And this brilliantly illustrates the core issue. On one hand, we have standard Markovian inference. The next output relies only on the current context window, leading straight to context exhaustion and semantic drift. But the actual solution to this is explicit causal history tracking. You must architect a system that records exactly why a decision was made, what alternatives were considered, and what constraints ruled them out. Yes, it comes with a 2 to 5 times memory overhead, but explicit provenance tracking is really the only known way to fix non-Markovian failures.
We see a similar structural shift here, too. Standard step-by-step agents decide their actions locally, which leaves them highly vulnerable to behavioral and semantic drift over those long horizons. But research by Shanofsky and Dror proves that a plan-ahead architecture fundamentally changes the game. By forcing the agent to construct an explicit plan before it starts executing, that plan acts as an unbreakable, reliable anchor against drift. It significantly mitigates several forms of semantic drift and premature termination, simply because the agent has a concrete map to hold itself accountable to.
So, to summarize these architectural prescriptions, there is no single silver bullet. To survive production, you need a combinatorial architecture. You need plan-ahead structures. You need state space models, like Mamba or hybrid attention for long sequences. You need causal history tracking. You need agents capable of executing multi-attempts with internal reflection. And you absolutely need post-failure trajectory-based root causing, like the AgentRx style. You need a combination of these 5 elements. Yet, as Mayer points out, remarkably few production systems today implement more than 2 of them.
Section 4. The Eval harness gap. Preventative medicine in production. This brings us to the final, and quite frankly, most critical gap we face. Because the truth is, you cannot fix what you cannot measure, and general benchmarks hide almost everything interesting.
The reality on the ground is pretty stark. A recent analysis by Digital Applied found that only 11% of mid-market teams running agentic deployments actually have mature evaluation harnesses. That means 89% of teams are completely flying blind. They are pushing complex autonomous systems into production without the ability to run targeted failure mode evaluations. They have no idea if their agent is going to collapse at step 47 until it actually happens in the real world.
To stop flying blind, an evaluation harness requires 3 very specific investments. First, trajectory replay tooling, pulling from methodologies like AgentRx, which allows you to replay a failed run and find the exact critical step where things went wrong. Second, targeted failure mode probes designed explicitly to trigger the 15 specific errors we discussed. And third, live production trajectory monitoring that actually detects failure patterns in real time, not just passively logging them after the fact.
So, the crucial point is the cost. To build a frontier-tier evaluation harness that fully implements those 3 investments, you are looking at a high-end cost of around $15 million. That's a massive number. But even for standard enterprise-tier deployments, teams absolutely must plan to spend at least $1 to $3 million just on their evaluation and monitoring infrastructure.
But the harsh truth Mayer reveals is that most teams have invested less than $500,000 in their evaluation harnesses. This massive underinvestment, this eval harness gap, is directly causing the "we've never seen this before" phenomena we talked about at the very beginning. It is currently the largest single source of entirely preventable production incidents in agentic AI today.
Think about it like this. Year 1 of production agentic deployments was basically a massive, chaotic data collection phase. Well, we now have the data. We have the taxonomy. The mystery is gone. The teams that adopt this vocabulary and invest seriously in rigorous eval harnesses are the ones who will capture the reliability gap and actually win enterprise trust. So, I leave you with this. The era of blind deployments is officially over. Are you and your engineering teams ready for the structured mitigation phase?